Okay, let's talk a little bit about pH and POH scales. There's a convenient way to express the acidity or alkalinity of a solution. We can use pH or POH. pH is certainly most common. Is defined as the negative logarithm of the hydronium ion concentration. The lowercase p is the negative log. It represents the function that we're doing, and then H is the hydrogen ion, which reflects the ion that's represented in the notation. But you could do the same thing with some other numbers. For example, the POH is the negative log of the hydroxide ion, and it's the inverse of the pH function because those ions are inverse of one another. But you could really do it with anything. The PAG is the negative log of the silver ion concentration, so on and so forth. We'll really focus on the pH and the POH though. So if I know either the hydronium ion or the hydroxide ion, I can get the pH, the POH. Really, if I know one of those four things, I can get the other three. So let's calculate the pH of a solution in which the hydronium ion is 0.030. So we're going to look at the paper. So we got hydronium ion equals 0.030 molar, and pH is equal to the negative log of the hydronium ion concentration. So that's going to be negative log of 0.030. So we're going to run that through our calculator. Negative log 0.030, and we're going to get a pH of 1.5. But what you have to notice is that the pH works on a base 10 because the log is a base 10. Change of 1 pH unit represents a factor of 10 in the change in concentration. If, for example, hydronium ion were neutral, which is 10 to the negative 7th power, as we talked about in our Kw expression, pH is negative log of 10 to the negative 7, and so the pH is 7. So essentially you're grabbing that exponent, if you have a straight power 10, flipping the sign, and you get the pH. When it's not quite on a power of 10, it's going to be close to, you see that's in the 10 to the negative 2 range, and so that what you'd say 2, but it's a little bigger than that, so it's 1 point something. All right, so let's look at another example. Let's say we got a pH now of 4.597, and we want to know the hydronium ion concentration. So essentially we're doing the reverse of what we were in the previous example. So if I do some inverse math on that, we find that the hydronium ion concentration is equal to 10 raised to the negative pH power. And so it's just, I've solved this equation for the opposite variable. So we've got 10 raised to the negative 4.597. And so then we're going to run that through our calculator. And we're going to put that in scientific notation. We're going to say 2.53 times 10 to the negative 5th. And that's a molarity. Even though pH tends to be presented without units, we need to put the unit back on it when we get to the concentration. Okay, we can have a convenient relationship between pH and pOH that can be derived for all dilute aqueous solutions at 25 degrees Celsius. We can say, if you recall our equation from our KW talk, if you don't remember that, go back and watch my KW talk. But past that, hydronium times hydroxide ion concentrations is 1 times 10 to the negative 14th power. If we take the logarithm of both sides, we get the log of H3O plus log of OH minus equals negative 14. Remember, if two terms are multiplied, the argument of logarithm is the same as adding two logarithms according to the laws of the logarithms. We take negative 1 on both sides, and we got negative log of hydronium, negative log of hydroxide equals positive 14. But we know that those negative logs mean something, so we can say pH plus pOH equals 14. Now I've got a relationship between pH and pOH. Well, even if you don't remember the derivation, make sure you remember that pH plus the pOH equals 14. So now I've got equations where I should be able to convert any of the four things that we've talked about, hydronium and hydroxide ion concentration, pH and pOH, as long as I know everything. So let's take a look at this example. If we got a 0.02 molar HNO3 solution, we want to get all four of those things. So since I'm talking about a strong acid, what I know is that the H3O plus concentration, since it's a strong acid, HNO3, 0.020 molar. Now, I can get the pH from that. You can go about this more than one way. So we're going to take the negative log of that. And that'll be 1.7. Hydroxide ion, as we've mentioned from the KW presentation, is going to be 1.0 times 10 to the negative 14th divided by 0.020. So run that through our calculator. And it's going to be 5.0 times 10 to the negative 13th molar. Now at this point, I've really got two ways to get at the pOH. It'll be simpler to get it from the pH. So remember, the sum of those two is 14, so pOH is going to be equal to 14 minus the pH, which is 1.7. Which will be 12.3. And so what we can see is that since water, the hydronium ion and the hydroxide ion equal 1.0 times 10 to the negative 7th, that's neutral water, then the pH of neutral water, this is for neutral water, equals the pOH, which equals 7. But this is nitric acid, pH 1.7. So that must mean that pH is below 7 or acidic, pH is above 7 or basic. The reverse is true for pOH, since I'm talking about the other ion. pOH is less than 7 or basic, but pOH is greater than 7 or acidic. And you can see the same thing If you got a greater hydronium ion concentration than that, which I do, it's going to be acidic. Less than that, it's going to be basic, and the reverse is true for hydroxide. So let's talk about the pH again. We talked about some of this a little bit with the example, but most solutions, the hydrogen or hydronium ion is small, so we define the pH as negative log of the hydronium or hydrogen ion concentration. The POH is negative log of the hydroxide. So neutral water pH equals POH equals 7. So in acidic solutions, the hydrogen or hydronium ion is greater than 1 times 10 to the negative 7, so pH is less than 7. In basic solutions, the hydrogen ion is less than 1 times 10 to the negative 7, so the pH is greater than 7. The higher the pH, the lower the POH. pH and POH values normally go between 0 and 14. There are no theoretical limits, though. 2 molar HCl has a pH of negative 0.301. So here are some common substances. 0.1 molar sodium hydroxide is about 13. Household bleach, about 12.5. Household ammonia, a little less than 12. Lime water, about 10.5. Milk of magnesia, a little under 10. Baking soda, about 8.5. Seawater, a little under 8. Human blood, 7.4. Rain is getting a little acidic, around 6. And that's normal rain, not acid rain, because it dissolved carbon dioxide from the atmosphere. Black coffee, about a 5. Soft drinks and vinegar, right around 3. Lemon juice, just a little above 2. 0.1 molar HCl, about a 1. But you can see that the pH and the POH are inversely related. Up here at a pH of 14, hydrogen ion is 1 times 10 to the negative 14th, and you've got a 1 molar hydroxide ion concentration. But as hydrogen ion gets bigger, hydroxide ion gets smaller. And the same with the pH and the POH.